Beams. So here you can see what are the types of beams. Beams are usually said to be members that support transverse loads. That means like this is the member, the loads are like this in the transverse direction. This is the support. So beams are said to be members that support transverse loads. So these are the transverse loads, right? They are probably thought of as being used in horizontal position subject to gravity or vertical loads, but there are frequent exceptions. Roof rafters, for example. Among the many types of beams are joists, lintels, spandrels, stringers, and floor beams. Joists are the closely spaced beams supporting the floors and roofs of buildings, while lintels are the beams or spannings in masonry walls, such as windows, doors. Spandrel beams support the exterior walls of the buildings, perhaps part of the floor and hallway loads. The discovery that steel beam was part of a structural frame could support masonry walls, together with the development of passenger elevator, is said to have permitted construction of today's high-rise buildings. Stringers are the beams in bridge floors running parallel to the roadways, whereas floor beams are the larger beams in many bridge floors, which are perpendicular to the roadway of the bridge and are used to transfer the floor loads from the stringers to the supporting girders and trusses. The term girder is rather loosely used, but usually indicates a large beam and perhaps one into which smaller beams are framed. These and other type of beams are discussed in sections below to follow. Sections used as beams. The W shapes will normally prove to be most economical beam section. They have largely replaced the channels and S section for beam usage. Channels are sometimes used for beam subject to light loads such as purlins and in places where clearance available require narrow flanges. They have very little resistance to lateral forces and need to be braced, as illustrated by sag rod problem in chapter 4. We will see the W shapes have more steel concentrated in their flanges than do S beams. Thus have larger moments of inertia and resisting moments for the same weights. They are relatively wide and have appreciable lateral stiffness. The amount of space devoted to S beams in AIC manual clearly shows how much their use has decreased from former years. Today, they are used primarily for special situations, such as when narrow flange widths are desirable, where shearing force are very high, or when the greater flange thickness next to the web may be desirable, where lateral bending occurs as perhaps with the crane rails or morals. Another common type of beam section is open web steel joist or bar joist, which is discussed at length in chapter 19. This type of section, which is commonly used to support floor and roof slabs, is actually a light soft fabricated parallel cord truss. It is particularly economical for long spans and light loads. Bending stress. For an introduction to the bending stress, the rectangular beam and stress diagrams are considered. For the initial discussion, the beam's compression flange is assumed to be fully braced against lateral buckling. Lateral buckling is discussed in some different chapters that we will see. If the beam is subjected to some bending moment, the stress at any point may be computed with the usual fractional formula FB equal to MC by I. It is to be remembered, however, that this expression is applicable only when the maximum computed stresses in the beam is below the elastic limit. The formula is based on the usual elastic assumptions. The stress is proportional to strain and plane section before bending remains plane after bending. Plane section after bending also. The value of I by C is constant in a particular section and is known as the section modulus. The fractional formula may be written as FB equal to MC by I, M by S. So here you can see this how the bending stress varies. Variations in bending stress due to increasing moment about x-axis. Initially, when the moment is applied to the beam, the stress will linearly vary from the neutral axis to the extreme fibers. The situation shown in part B of the figure 8.1. If the moment is increased, there will continue to be a linear variation of a stress until the yield stress is reached in the outermost fibers. Fe becomes Fy until the yield stress is reached outermost fibers as shown in the part C of the figure. The yield moment of a cross section is defined as the moment that will just produce the yield stress in the outermost fiber of the section. Yield moment means that outermost fiber is reached just to produce the yield stress in the outermost fiber section. If the moment in a ductile steel beam is increased increased beyond yield moment, the outermost fibers that had previously stressed to the yield stress will continue to have the same stress, but will yield, and the duty of but will yield, and the duty of providing the necessary additional resisting moment will fall on the fibers nearer to the neutral axis. And this process will continue with more and more parts of the beam cross section is stressed. So the yield stress as one in the stress diagram spot E, D and E, until finally a fully plastic distribution is approached, as shown in part F. Note that the variation in strain from the neutral axis to the outer fiber remains linear for all these cases. Note that the variation in strain from neutral axis to outer fiber remains linear for all cases. When the stress distribution has reached at this stage, a plastic hinge is said to have formed, because no additional moment can be resisted at this section. No additional moment can be resisted at this section. Any additional moment applied in the section will cause the beam to rotate and it will increase then with little increase in stress. The plastic moment is the moment that will produce full plasticity in a member cross section and create plastic hinge. The ratio of plastic moment to yielding moment is called shape factor. The shape factor equals 1.5 for rectangular section and varies about 1.1 to 1.2 for standard rolled beam sections. Plastic hinges. This section is devoted to a description of the development of plastic hinge. As in the simple beam shown in figure 8.2, the load shown in applied to the beam and increase in the magnitude until the yield moment is reached and outermost fiber stress to the yield stress. The magnitude of the load is further increased with the result that outer fibers begin to yield. The yielding spreads out to the other fibers away from the section of maximum moment, as indicated in this figure. The distance in which this yielding occurs away from the section in question is dependent on the loading condition and the member cross section. For a constant load applied at the center of the simple beam with rectangle cross section, yielding in the extreme fibers at the time the plastic hinge is formed will extend for 1/3 of the span, and for a W shape in a similar circumstance, yielding will extend for approximately 1/8 of the span. During this same period, the interior fibers of the cross section or the section of maximum yield gradually until nearly all of them have yielded plastic hinges formed. Although the effect of plastic hinge may be extended from some distance along the beam, for analysis purpose it is assumed that to be concentrated at one section. For the calculation of diffractions and for the design of bracing, the length over which yielding extends is quite important. For the calculation of deflections and for the design of bracing, the length over which yielding extends is quite important. For plastic hinges to form, the sections must be compact. This term was previously introduced in section 5.1. The compact sections were defined as being those which have sufficiently stocky profiles such that they are capable of developing fully plastic stress distributions before they buckle locally. This topic is contained in some detail in section 9.9. The student must realize that for plastic hinges to develop, members must not only compact but also must be braced in such a fashion that lateral buckling is prevented. Finally, the effects of shear torsion and axial loads must be considered. They may be sufficiently large as to cause members to fail before plastic hinge can form. In the study of plastic behavior, strain hardening is not considered. So strain hardening is not considered in the study of plastic behavior. Elastic design. Until recent years, almost all steel beams were designed on the basis of elastic theory. The maximum load that the structure could support was assumed to equal to the load that first caused the stress somewhere in the structure applied equal to the yield stress of the material. The members were designed so that the computer bending stress for service loads and did not exceed the yield stress divided by the structure safety. Engineering structures have been designed for many decades by this method with satisfactory results. The design professional, however, has long been aware that ductile members do not fail until a great deal of yielding occurs after the yield stress is first reached. Until the great deal of yielding occurs after the first yield stress is reached. This means that such members have greater margins of safety against collapse than the elastic theory, which would seem to indicate. plastic modulus. The yield moment My equals to the yield stress times elastic modulus. The elastic modulus equal to I by C equal to BD squared by 6 for rectangular section. The yield moment equals to BD squared by 6 Fy into BD squared by 6 because the distance is 2 by 3 into D, right? This table you can be obtained by considering the resisting internal couple. This is 2/3. C is from here 1/3, from here 1/3, right? So 2/3. 1 by 2 into half of this triangle is half into this one is vertical height is d by 2. This is b half and Fy into d by 2 into b. So Fy into b d by 4. Fy b d by 4 into resisting moment equal to tension or compression times arm between them. Resisting moment, tension or compression times the arm between them as follows. My equal to Fy b by d into 2 by 3 into d, that is 2 by 3 into d is here. So F by b d squared by 6, the elastic section modulus can again be seen equal to b d squared by 6 for rectangular beam. The resisting moment at full plasticity can be determined in a similar manner. The result is so-called the plastic moment. It is also the nominal moment of the section. Plastic or nominal moment equals T or C times the linear arm between them. For the rectangular section, we can have T into D by 2 or C into D by 2, Fy BD by 20 D by 2, Fy BD squared by 4. So here, the plastic moment is set to equal to the yield stress times the plastic section modulus. From the foregoing expression for rectangular section, the plastic section modulus Z can be seen equal to BD squared by 4. The C factor is equals to MP by My, Fy is Z by Fy into S, or Z by S equal to BD squared by 4 or BD squared by 6 equal to 1.5 for rectangular section. A study of the plastic section modulus determined here shows that it is equal to the static moment of the tension or compression about the areas over the plastic neutral axis. Unless the section is symmetrical, the neutral axis of plastic section will not be in the same location as for the elastic condition. The total internal mass, internal compression must equal to the internal tension. As all the fibers are considered to have the same stress in plastic condition, the areas above and below plastic must be equal. This situation does not hold for unsymmetrical sections. Elastic condition. Example 8.1 illustrates the calculations necessary to determine the safe factor for a T beam on the nominal uniform load WN that can be theoretically supported. Here we can see a modulus of a structural T beam. Also calculate the safe factor, the nominal load that can be placed on the beam. Simple span 50 KSA. Elastic section, elastic calculations. Area is nothing but 8-inch, 1 by 1 inch, correct. 6-inch, 2 inch. This is also correct. Y bar equal to 12-inch into 0.75 plus 12-inch 4.5 inch by 24 inch. That is the area. This is the area. All right. So 0.625 inch from the top of lunch. I equal to 1 by 12 into 8 inch into 1.5 cube plus 8 inch into 1.5 into 8 point square 1 by 12 into 2 into 2 inch into this value 2 inch 6 inch 1.875 is simply the I value. Once we know the I value, then we can see the S value. S value is nothing but I by C. So 122.6 divided 4.225. My is yield moment is Fy into elastic section modulus. So we have 104. Plastic section modulus. Plastic neutralizes at the base of the flange. Plastic neutralizes at the base of the flange. Z equal to 12 inch squared into 0.75. Inch squared into 3 inch. N equal to MP. Plastic moment equal to Fy into Z. So say factor CMB by My Z by S, that is 1.79. M in nominal what is W? L squared by 8. So W into L squared by 8, this value.